In this example, we're going to be using properties of logarithms to expand each expression. So in a here, we have log base 5 of, in parentheses, a squared times b squared. Because these two expressions are connected by multiplication, if we want to expand it, we will expand it into two logarithms, separating the logarithms by addition, according to the product property of logarithms. Like so. The last thing we have to do for expansion, if possible, is if there is an exponent according to the power property of logarithms, we want to move it down into the front. So we'll take each of our exponents and move them down into the front as a coefficient with a logarithm. So 2 log base 5 of a plus 7 log base 5 of b. Now for the second logarithm, the natural log of 25 over 3, you'll notice that this one deals with numbers, and 25 happens to be a perfect power. So oftentimes, if a number is a perfect power, you will rewrite it as something to a power. In this case, 25 is 5 squared. And then because these two numbers on the inside of the logarithm are connected by division, we will use the quotient property of logarithms to separate and expand it into two logarithms of ln of 5 squared minus ln of 3, according to the quotient property. And lastly, because we do have an exponent with the 5, we will drop it down in front of the logarithm to be 2 ln of 5 minus ln of 3. And there we have it. So in this example, we're going to be using logarithm properties to write multiple logarithms as a single logarithm. Now, in order to do this, in order to use the product or quotient properties, the two logarithms must be connected by addition or subtraction, but there can't be any coefficients with them. So in A here, if we glance through A, we can see that we have a coefficient of 4, a coefficient of 3, and then just a minus sign, coefficient of 1 if you prefer. Because we have a coefficient of 4, we want to move it up as an exponent, because as is, we can't combine them into a single logarithm. The power property of logarithms allows us to do this. So we'll rewrite the first logarithm as log base 4 of m to the power of 4. The second one we'll rewrite as log base 4 of n to the power of 3. And the third logarithm, that didn't have a coefficient, so we'll leave it alone. Next, because we do have 3 logarithms, we'll just group 2 of them together at a time as we move from left to right. So the first 2 logarithms are connected by addition. Since they are connected by addition, when we write them as one logarithm, we are going to apply the product property of logarithms, which says that when 2 logarithms are connected by addition, we can write them as a single logarithm with the insides connected by multiplication, like so. We still have the minus log base 4 of p. Now log base 4 of p is connected to the other logarithm by subtraction, which means if we want to write it as a single logarithm, the insides will be connected by division. So we'll have m to the power of 4 times n to the power of 3 over p, and there we go. The second one on the right has numbers on the inside of the logarithms, but we still start off with the same approach, get rid of the coefficients. So we will move the 3 up as an exponent, making an ln of 2 to the third. But wait, 2 to the third, we can actually do something with that. 2 to the third is 8. So ln of 8 is what we actually have. The second logarithm, we can move the coefficient up. Technically, we can move the negative up as well, but it doesn't really change where we end up, so I usually don't. So if I move the 2 up as an exponent, as 5 squared, but 5 squared, once again, we can actually do something with. 5 squared is 25. Now that we no longer have coefficients on the outside of logarithms, we can write the 2 logarithms as a single logarithm. So according to the quotient property, since they are connected by subtraction, when we write it as one logarithm, their insides are going to be connected by division. So ln of 8 over 25 is the final answer. Okay, in this example, we're going to be evaluating log base 5 of 100. So if I go to the right screen, that is. Let's just close that off. So log base 5 of 100, depending on what calculator you have, depends on how the difficulty in actually doing this. So for example, this is Desmos right here. Desmos, you can find any logarithm, log of any base in the menu here. ln is the natural log. Log is log base 10. And then they have this extra key, log base a. So if we click on log base a, it will allow us to enter a subscript. So I can do 5 of 100. So that's the value for log base 5 of 100. Now, the problem lies in actually having this key. Not all calculators have a log base a key, and most of the ones that do have the ability to do this directly have it in a menu that can be very hard to find where it is, or very time-consuming to find where it is. So how can we evaluate this if we don't have access to log base a key? Well, log base 5 of 100 can be evaluated using the change of base formula. The change of base formula says that if we have log base b of m, then we can do log base a of m divided by log base a of the original base. So this allows us to change the base from the original logarithm to a new base that we may be able to use just by doing the inside of the logarithm divided by the base, taking the log of each of those different numbers. So what this means is we can turn log base 5 of 100 into a log base 2, for instance. So I can do log base 2 of 100 divided by log base 2 of 5. Now, log base 2 isn't very helpful either because most calculators don't have a log base a key, which means you couldn't do log base 2, and which would make trying to do it this way completely pointless. But a lot of calculators do have the log key, so we can do log base 10 of 100 divided by log base 10 of 5. Or they have the ln key, which is ln of 100 over ln of 5. Now, one of these two is the typical one that people will say. Usually it just depends on who teaches you as far as which one they tell you to use. There is not actually a difference, and I'm going to show you in just a second. So it really comes down to just personal preference. I prefer typically to use the ln key. But if I head back over to Desmos and just show you all three of those and compare them to that original value. So functions, I'm going to do the one I wrote up originally, apparently not a new line because I wasn't paying attention. Okay, so new line. Division, functions, log base a of 2 as my first example I gave. Functions, log base a of 2 again of my original base 5. You can see that they're the same thing. If I do log base 10 of 100, which I already know is 2, divided by log base 10 of 5, you can see that they're all the same so far. And if I try that last one that I gave, ln of 100 divided by ln of 5. And you can see that all of them give us approximately 2.861, no matter which version you use. So approximately 2.861. Do be very careful when you try to use this property, typing it into the calculator. Depending on how your calculator is, depends on how you want to type it in. For example, if it doesn't do order of operations for you, you may have to do it in pieces as the nicest way. Just evaluate the top, evaluate the bottom, and then divide. If it does do order of operations for you, you'll probably have to make sure you enter parentheses. So if I show you the parentheses, so for ln of 100 divided by ln of 5, making sure you close the parentheses. A lot of calculators will open the first set of parentheses for you automatically. So if you don't close them, it will not have the right formatting. So just make sure you understand how your calculator that you use to do this actually works. But other than that, it's pretty straightforward once you get the hang of which number goes where. So, and it doesn't matter, again, which logarithm you choose, so long as you can actually use that logarithm on the calculator.